AS Unit 2, Topic 2, the second part of the topic is on isomers. First of all, we're going to look at some structural isomers and then we're going to look at some geometric isomers. There are three types of structural isomers associated with organic compounds. Compounds that have structural isomers have the same molecular formula but a different structural formula. We're going to look at three different examples: chain, positional, and functional group. If we look at chain isomers, we can see butane and 2-methylpropane have the same molecular formula, but a different arrangement of the atoms in a carbon chain. As we increase the number of carbons in the chain, the number of possible isomers increases rapidly. Positional isomers are where the molecules have the same functional group, for example, the double bond in pent-1-ene and the double bond in pent-2-ene, but it is at a different position in the molecule. Another example of positional isomers, it occurs in alcohols, and you met this example at GCSE, where you have propan-1-ol and propan-2-ol, both that have the same molecular formula but a different structural formula. The third type of structural isomer we're going to meet are called functional group isomers. For example, ethanol and methoxymethane both have the same molecular formula, but they have different functional groups. The next example is one we will see at AS level. We have here aldehydes and ketones. In this case, both have the molecular formula C3H6O, but they are different functional groups. A third examples are esters and acids, and you can see the example. They both have the same molecular formula, but they have a different functional group. We are now going to look at a type of stereoisomerism called geometric isomers. Stereoisomers have the same molecular formula, but the atoms occupy different positions in space. To have a geometric isomer, one of the conditions you require is a carbon-carbon double bond. Single covalent bonds can easily rotate. However, when you have a carbon-carbon double bond, you have restricted rotation. This lack of free rotation about the double bond causes some alkanes and substituted alkanes to exhibit geometric isomers. The first condition for a geometric isomer is to have a carbon-carbon double bond. However, not all alkanes form geometric isomers. The second condition is that on each carbon you must have two different atoms or groups attached. If you have a look at this slide, you can see that the first example, each carbon has two different groups attached, but the second and third molecule on the first carbon, they have the same groups attached, so they do not exhibit geometric isomers. The final example is where you have different atoms and groups attached on each side, and it also exhibits geometric isomers. Here is but-2-ene. If you look at the two molecules drawn, you can see that they have a double bond, which is one of the conditions for geometric isomers, and on each carbon they have two different groups attached. In the first drawing of but-2-ene, you can see that the methyl groups are on the same side, and on the second example, you can see that the methyl groups are opposite each other. If we want to name these isomers, when the methyl groups are on the same side, we call that a cis isomer or a sed isomer, which is German for cis-man, which means together. And in the second one, they are opposite each other, so that is called trans, or we use the letter E, and that comes from the German entanglen. We tend to use cis and trans when we have a hydrogen on each carbon atom. We use E and Z when we have different atoms on each carbon. If we look at this example, you can see that it does not exhibit geometric isomers because it does not have different groups bonded to each carbon atom. If we have a look at these molecules, we are going to assign them as E or Z. In the first example, the methyl groups are opposite each other, so that is an E isomer, and in the second example, the methyl groups are on the same side, so that is a Z isomer. We put the letter before the name and we use a dash between the letter and the name. Entangin, remember, means opposite, and cis-min means together. What happens if we don't have a hydrogen attached to each carbon? This makes it a bit harder. What we have to do is we have to look at the atomic numbers attached to the carbon-carbon double bond. The higher values, if they are opposite, become an E, and if the higher values are on the same side, it becomes a Z. Here is an example. If I look at bromine, bromine has a higher atomic number than fluorine, so we give it the priority number 1. If I look on the second carbon, I have chlorine and hydrogen. Chlorine has a higher atomic number, so I give it a priority of 1. In that case, the bromine and the chlorine are the higher priority groups and they are on the same side, so that isomer must be a Z. In the second example, the bromine and the chlorine are opposite each other, so that must be an E isomer.